All right. Welcome everybody. I am very happy to see you. Well, I don't see anybody except for Lyndon, but I'm very happy to have everyone here on this call. I am very happy to welcome you to the MoCaO lecture series of 2026 and introduce our speaker for this series, Lyndon Roberts. And before I continue, I suppose I should introduce myself, right? My name is Dmitro Matsipura, and I am a core chair on optimization of MoCaO, which is the interest group of OSTMS on mathematics of computation and optimization. And once again, I am very happy to introduce our speaker this year, Lyndon Roberts. Lyndon is a senior lecturer and an ARC Decker Fellow at the School of Mathematics and Statistics at the University of Melbourne. He is also a chief investigator for MathQuest and the associate investigator for Optima. He is, broadly speaking, interested in algorithm development, implementation, and analysis, right? Broadly speaking, in nonlinear optimization. And today, we're very fortunate to have Lyndon talk about the derivative-free optimization. And I thought that Lyndon, being an expert in that side of the optimization, would be a great treat for all of us to hear him talk about something he's very passionate about. He has published quite a few papers on the topic. And Lyndon, thank you very much for agreeing to do this. Uh, we are looking forward to what you have to say.
Great, thank you very much for the kind introduction. And let me just get my slides working. Can you see that okay? The full screen
Yes, we do.
version? Okay, excellent. So yeah, thanks for the introduction. Thanks for having me. And yes, this is, I guess, a sequence of, well, I'm going to be speaking for 3 sessions. So at this time, tomorrow and Wednesday as well, on model-based derivative-free optimization. I will start from the beginning so we understand what all of this is. And so, yeah, this is going to be talking about the mathematics of model-based derivative-free optimization. That's, as the name suggests, it's part of derivative-free optimization as a broader category. I'm not going to assume any familiarity with DFO in any sense. So in terms of what I'm hoping for this week, so today I want to start quite basic, motivation, applications, some of the other types of DFO methods that aren't model-based, and just to kind of have a fairly gentle introduction. Tomorrow is going to be some of the kind of key theory that underpins all these methods, and then on Wednesday, I hope to go into some of the more practical aspects that still have mathematical theory, but we start to kind of push towards things that are actually useful in kind of real world problems. Then on Thursday and Friday, so the time switches from 2 p.m. Eastern time to 11 a.m. Eastern time for Thursday and Friday. On Thursday morning, we've got Zaikun Zhang, who's based at Yat-sen University in China, and he'll be talking about some of his work on large-scale model-based derivative-free optimization. So how do you extend these methods to problems where the dimensionality is a bit higher? And then on Friday morning, we've got Sara Shashaani from North Carolina State. I apologize for the typo. Who's going to talk about stochastic problems, particularly simulation-based optimization problems, which I'll talk a little bit about on Wednesday. But Sara is really an expert on that sort of stuff. Okay, so that's the plan for the next few days. I should say, please feel free to just interrupt me at any time. I'll try and save some time at the end for questions, but I'm happy to be interrupted whenever you like. Okay, so in terms of what I'm going to talk about, conveniently, I did actually put together a summary on this topic late last year. So you can, the structure I'm following here is very close to what I used in that reference that's on arXiv. But in terms of the other sorts of kind of key references in this area, if you want to explore some more, there's a nice book by Charlotte Day and Warren Hare, Derivative-Free and Black Box Optimization, that the second edition just got published, I think, less than a month ago, which is kind of aimed very broadly on this topic. It's designed for kind of like late undergraduate, early PhD. It's a very accessible text with a little bit on model-based methods. The kind of, for me, kind of the Bible reference book for the model-based topic specifically is this book from 2009 by Andy Kohn, Katja Scheinberg, and Luis Vicente, which sort of encapsulates a lot of the theory that they developed that really underpin this area. And if you want a very, very broad survey, like a literature survey, there's this nice Acta Numerica article from 2019 from Jeff Larson, Matt Manichelli, and Stefan Wild. But I'm really going to be following the stuff that I wrote up last year. Okay, let's kind of slowly kind of make our way towards what model-based DFO is in general. I'm going to start very, very straightforward. I'm not going to assume a lot of background at this point. So I'm going to start with very, very simple undergraduate type setting of gradient descent. So most of the week, we're going to be looking at just this unconstrained problem in Rn. So f is usually going to be a smooth function. So we're going to assume usually C1 with Lipschitz gradients. And just to kind of step us through for the people that aren't too familiar with optimization, the gradient is going to point in the direction of fastest ascent, at least locally, for any given point x. And so if we want to minimize the function, we want to move in the opposite direction of fastest descent, and we get the gradient descent algorithm, where if we're at a point xk, we take some positive steps, alpha is some positive step size, in the negative gradient direction to get our next iterate. I'm sure pretty much everyone's seen this, but just in case you haven't, there's many different things you can say about it. But for example, a sort of classic result might say if you've got a C1 function that's bounded below and its gradients are Lipschitz continuous with a constant L, then one way you can make this method work is you set your step size to be 1 over L, and then you can prove that the sequence of gradients you're going to follow goes to 0 regardless of the starting point that you work from. There's many other results you can mention, but this is kind of a basic one. And if you want to make more assumptions like convexity or various other things, then you can get stronger results. So, iterates converging, for example. If we want to go one notch up, we can think about where this gradient descent method comes from. And if we say direction of fastest ascent or descent locally, the way you kind of prove that is by looking at a linear Taylor series expansion. If you want to go one level up and use quadratic Taylor series expansion, so if you have access to second derivatives, then obviously you can get a more accurate Taylor approximation for your function by considering the standard quadratic Taylor series for f at xk. And what you could do, for example, is if this Hessian is positive definite, then this approximation as a function of s is a convex quadratic. And so if you want to minimize f, you could instead minimize the approximation, minimize a convex approximation. And so you take the derivative with respect to s, set that to 0, and you get Newton's method. And again, we can pick a step size in some way as well. So now our update says we start at xk, we then solve a linear system that's Hessian times step equals the negative gradient, and then we take a step of length alpha in that direction. And again, various theoretical results that you can say. For example, if you've got a C2 function, obviously if we're using Hessians, we've got a C2 function, and we've got Lipschitz continuous Hessians. And for example, if we're close to a local minimizer with a positive definite Hessian, and if we start sufficiently close and we pick alpha is 1, then we're going to converge quadratically. So we can usually get better results in practice, at least. In theory, there's a little bit of debate in what situations Newton's method is provably faster than gradient descent, but here's an example where it is. So these are some very, very classic methods. I expect pretty much everyone's seen something like this before, but I want to mention it just in case you haven't. So now let's think about the practicalities. We want to actually implement these methods, right? We want to implement either gradient descent or Newton's method for the function of our choosing. Well, one of the first things we're going to run into if we try and implement this is we're going to need access to the derivatives of f, either just the first derivatives or first and second derivatives, depending on what we want to do. And so it seems reasonable that we should at least be able to implement the objective function we're trying to minimize. That feels like a bare minimum requirement if we're trying to implement an optimization method, is that you can give me the thing you're optimizing. But if we want to use these algorithms, we need to provide more information. We need to provide the derivatives. So if we assume we have access to f of x, how do we get the derivatives? Well, there's basically 3 approaches you could do. If f is simple enough, you can just write down the formula for it. You can differentiate it by yourself or using Mathematica or something, and then you can write down the function. You can implement that by hand. If f is too complicated, that's not really so practical. So you could do something like finite differencing, where you take small perturbations of f and approximate gradients. And there's similar approximations for higher order derivatives that look something like this. Or if you've got access to the right tools, particularly if you do machine learning, these are completely standard. You can use what's called backpropagation if you're machine learning, algorithmic or automatic differentiation if you're in kind of numerical analysis. And what that does is they're very kind of sophisticated software tools that what they can do is take your code for evaluating f of x and essentially produce code that evaluates gradients. So it's sort of a form of symbolic differentiation, but it does it kind of step by step through the actual software, through the code implementation of your f of x, essentially working through the source code line by line and using the chain rule. So it produces a piece of code that evaluates the gradient. And these aren't approximations. These are genuinely the actual derivatives. They're not finite difference approximations. And if they're implemented well, such as in the standard machine learning libraries, then this is a very, very powerful tool. I would strongly recommend not implementing this yourself unless you have several years to spare. This isn't always possible. So we need something like one of these methods, but this isn't always something that we can get. So if you've got a function that's black box, so there's some component of it that you can't look into, you don't actually know what the equation is, you maybe don't have access to the source code of at least some component of your function, then that rules out the possibility of writing things by hand or backpropagation. And you're essentially left with approximations like finite differencing. In that situation, if you've got a function that's either computationally expensive or noisy, so by which I mean some degree of uncertainty in the evaluations of f, then this finite difference approximation isn't necessarily such a good idea. If we've got an n-dimensional function, to compute a full gradient means we need to perturb f along each of the coordinate axes to get each component of the gradient. And so for an n-dimensional function, that's going to require n+1 evaluations of f, including the n perturbations and the original base point to get a full gradient. That might not be so easy to do if you've got a very expensive function to evaluate. If you've got noise, the fact that you're subtracting the values of f at two nearby points means you can have the noise reinforcing and you can lose quite a lot of accuracy in the gradient approximation. So these are the sorts of situations where, in principle, you could try and compute some gradients, but it might not be very practical. It might not be very accurate. And this is the world where DFO comes in. The other issue that we have to think about when we're implementing algorithms like this is this issue of picking the step size. If you're in machine learning, you'd call it a learning rate. The sorts of options that are available to you are things like, if we want to use alpha as just 1 over L, you need to be able to compute the value of L for the function of your choice. If you can't do that, particularly say the ML people might use hyperparameter tuning. They'll just try a variety of choices of alpha and pick one that seems to work. If you're more sophisticated and your problem is straightforward enough, there are also adaptive procedures, things like line searches, where at the current xk, you automatically go through a process to pick a good choice of alpha at this current point, often by imposing things like sufficient decrease, so things like line search procedures. And in general, I'm not going to talk about anything other than the adaptive procedures. I want something that doesn't require any hyperparameter tuning, especially if you're optimizing something that's expensive to begin with. You don't want to be running the optimization multiple times. We want something that sort of adapts to how we're going in the progress of the algorithm, so something that's going to adapt to the local curvature of the function. And if we're in a derivative-free setting, I think it's very unlikely there's going to be many situations where you know things like Lipschitz constants in advance. If you can't get the gradient, it's unlikely you're going to be able to compute a Lipschitz constant either. So in all this situation, we're going to look at a situation where we want to minimize a function, but we don't have access to gradients. Now, the function might still be differentiable. We just aren't allowed to access its gradient information for one of those reasons that I mentioned. And so derivative-free optimization, DFO, is a way of doing that. So we're going to assume we can evaluate the function, but not its gradient, Hessians, whatever else. For the theory I'm going to present here, I'm going to assume that f is differentiable. If you want a slightly more complicated situation to look at, is the idea of a comparison oracle. So that's where we even lose access to f of x. So all I'm going to know is if you give me an x and a y, I can tell you if f of x or f of y is smaller, but I can't give you any numerical values. So I can't tell you how much better. I can just say they are better. A nice example might be if you go out and do a survey where maybe you're not particularly happy, where you just kind of ask people their preferences rather than getting a clear measure of which one's better by a certain amount. Again, the focus here is going to be on local minimization. So we're going to try and find local minima rather than global minima. In theory, we're not necessarily going to be able to get local minima. We're going to ask for approximate stationary points. So we're going to drive our gradient towards 0. And again, we want efficient adaptive methods. So we want things that work well as have nice mathematical theory attached to them. Okay, so I said this is the setting that we might be coming across, but this is kind of pointless unless we can identify that there are actually settings where this stuff doesn't become available. So let's just look at some examples. So first example, this is some work that I've been involved with for a few years now on climate modeling. And here it's a very, very simple problem from an optimization standpoint. We've got a model for the global climate. So this is a measure of how atmospheric physics, how sea ice, how ocean physics kind of evolves through time across the world. And this is a model that's driven by a bunch of partial differential equations. These have unknown parameters. We have observations of the Earth's climate. So we're trying to find values of the parameters that match the observations. So it's just a standard sort of least squares fitting problem that's completely normal when you've got any kind of model fitting process. The reason this becomes a problem, though, is if we want to evaluate the model from my particular choice of parameters right now, that involves me simulating the global climate for something like 5 years at some degree of resolution to solve the PDE. That is very expensive. Typically, we're talking between 8 hours and 24 hours on a supercomputing facility. So we can't just run as many evaluations as we would like. And the underlying physics is extremely complicated. The PDEs are not straightforward to solve. We don't have access to symbolic derivatives like adjoint methods, for those of you who know what those are. We've also got chaotic physics, which essentially you can interpret as for very small changes of x, for very small changes in our parameters, we can get very large changes in what the model predicts. In effect, that means we've got a noisy function. So small perturbations in the function, in the inputs lead to large changes in the outputs. So we've got something that's expensive, black box, and noisy. And so if you try to run standard least squares fitting methods off the shelf, they just don't work. Other examples. So Dimitri mentioned MathQuest, which is mathematics for the quantum era. One use of derivative free at the moment is in solving discrete optimization problems using quantum computers. So imagine things like a traveling salesman problem, things like that. So the quantum approximate optimization algorithm, QAOA, the way that works is you take your discrete optimization problem and you reformulate it not in the specific, for example, LP or QP or whatever you like format, but you convert it to what's called a QBO, a quadratic unconstrained binary optimization problem, which looks something like what I've written down here. Once you've written your problem in this form, which is fairly straightforward to do, you can turn this into a maximum eigenvalue problem or a Hamiltonian type problem. And in QAOA, what you try and do is you try and optimize the continuous parameters of a quantum circuit. So quantum circuits are continuous objects. So quantum hardware that approximates the Hamiltonian evolution that derives from this QBO. And so the mathematical problem you get is something like a maximum eigenvalue problem. So except the phi of x represents the kind of the complicated relationship of the quantum hardware. And there's an expected value here because in practice, you're running things through quantum hardware, which means that all the measurements you get, all the outputs you get are stochastic. So essentially you get this kind of stochastic problem. And in the quantum world, in principle, there are ways of extracting derivative information, but certainly with the way the hardware is at the moment, this is not really practical to do. So we effectively treat this as a black box where we can only get function values. And we've also got noise from just the nature of quantum physics. So QAOA is a way of kind of converting discrete optimization problems to a continuous derivative-free optimization problem where the objective value is calculated on quantum hardware. Nice example from machine learning is adversarial example generation. So here, what you can look at is you can train a neural network, for example, image classification. And what you want to do is, given an image of your choice, you want to find a very small perturbation of that image, essentially one that's invisible to the naked eye, that forces the neural network to misclassify what you've done. So you can think of it as an adversarial attack on a neural network. If you're an adversarial attacker, you can assume that you probably don't know the neural network structure. You don't know all the weights. So effectively, this gives you a black box problem. If you know the weights, it's a derivative-based problem and it's much easier. And if you are an adversary, you might not want to test very many examples. You might not want to throw too many images at your neural network because you might get detected. So this is an example from one of the original papers looking at this phenomenon, where you take a trained neural network, you give it this image, it says it's a panda. You take a sort of epsilon perturbation. This is not random noise. This is very specific structured noise learned by the optimization. You get an image that looks to the naked eye identical, but your neural network is convinced you've changed what this image is. This isn't purely an adversarial thing. There was a lot of press a couple of years ago about a tool called Nightshade, which would allow artists to apply this exact technique to their own images before uploading it to Instagram and other social media, so that it's much harder for companies to scrape that and use it as training data. So it was a way for artists to protect their work against generative AI models. Another example which has a couple of interesting features is optimizing the production of styrene. So styrene is a component of polystyrene, and there's a chemical process for manufacturing this using a compound called ethylbenzene. You heat it, there's chemical reactions occur, you get distillation and so on. You can extract out styrene. But from a simulation point of view, what you've got is this whole heating process. There's a whole reaction and various things that happen. There's a bunch of numerical methods that are involved to simulate this. And you get quite a complicated, effectively a black box simulation here. And one problem that you could do is to optimize how you construct this procedure. So things like the dials that you use to control the temperature of the heating, the dimensions of the reactor, various other kind of components of this model. And there's a nice problem not to necessarily maximize the output, but to maximize the economic, let's say, sustainability of the process, maximize the profit if you're a manufacturer. And what you've got there is, obviously, there's a net present value calculation which uses this complex simulation as a subcomponent, but you've also got a bunch of constraints that might come up, things like maximum total investment, minimum purity of the outputs, and then other more complicated things like environmental regulations, because this is a potentially polluting process. And so what you end up with this particular problem is the objective has parts that are complex black box simulations, parts that are fairly straightforward. And you've got a bunch of constraints, some of which have nice simple forms. There might be bounds or linear constraints, some of which might have complex functions, black box functions themselves involved. And some of them are even harder. They're called unquantifiable constraints. So what that says, if you give me an input X, I go away and do something, and I just return a flag, yes or no. This set of X is feasible. This set of X is not feasible. I can't tell you anything about a distance to feasibility. I haven't got a function, a numerical value that we can work with. So unquantifiable constraints, which obviously you can imagine are much harder to work with because you've got so much less information. Last example I want to mention is something called simulation optimization. I mentioned this because Sara on Friday is an expert in this sort of topic. And here you naturally have problems that are written as an expected value, as an expectation. So I've got an F that depends on my inputs X and some source of noise omega, and I can only get them by simulation. So a really nice, simple example that I like to show, just because it's very easy for us to think about, is called the bus arrival problem. So the idea is that we've got some unit of time, t equals 0 to t equals 1, and a bunch of people, large number of people are going to be arriving randomly at this bus stop at random times. So following a uniform distribution between 0 and 1. At the end of this, at time t equals 1, there's going to be a bus that picks up whoever's there and takes them away. But what we want to do is we want to pick a second bus to come at some point in that time 0 to 1 and collect whoever happens to be waiting by that point. And what we want to do is figure out when should the second bus leave so that the average waiting time for all the people that turn up is going to be minimized. Now, for those of you that teach, this is actually a really nice little first-year probability problem. To get an analytic solution is just one integral. You end up with a convex quadratic function. But this problem does generalize to more complicated things. So I know someone, for example, that looks at optimizing the locations of ambulance bases in a city, where we're trying to minimize not necessarily the waiting time for people to arrive, but the time it takes for an ambulance to get from the base to wherever the emergency happens to be occurring, which again, you can think of as a spatially random and temporally random object. So this thing does get much more complicated in practical situations. So if we would imagine we didn't want to do an analytic solution for this problem, what we could do is pick a very large number of random arrival times and then for a given value of t, we could compute the average waiting time for those passengers, and that could give us a problem to minimize with respect to t. If we do that, though, this is an example I generated with 100 random people arriving. The average waiting time between, if the second bus goes between 0 and 1, looks something like this. So in the limit, this becomes a quadratic function. But for any finite number of samples, you get this very jagged behavior that kind of smooths out as you go. And it's not hard to do the analysis to see that although in the limit, the objective is quadratic, for any finite n approximation, the objective you get is piecewise linear and strictly increasing with just discontinuities that jump down. So it's a piecewise linear, strictly increasing function. What this means is that any attempt to compute analytic derivatives in any reasonable sense is always going to give you a positive number, which means the minimum should always be at 0. So here you can get derivative information, but they're actually completely useless, the derivative information. It doesn't actually tell you anything about the behavior of the function. It'll just send you kind of to the bottom of whichever kind of jagged bit you start at. So it's a simple problem, but the natural approach doesn't work at all. And I say more complex examples, you get these similar sort of behaviors arising with finite n behavior. So just in general, where these sorts of problems arise, if we want to think about where DFO is going to be useful, it's all of these situations I've mentioned. So somewhere where you've got black box components. So that could mean a very complicated simulation, something where you have to go out into the real world and actually do a physical experiment. You can't differentiate a laboratory experiment. Or, in our world, there might be situations where you're having to work with legacy code libraries that you can't apply automatic differentiation through. You've got to have interesting situations where you might have noise. So Monte Carlo simulations, chaotic dynamics, experimental error, from doing a physical experiment, and or something that's expensive to evaluate. And this is one that is very much problem dependent. Expensive to evaluate can mean things both like the time it takes, the amount of compute resources that's required, a dollar value associated with the cost of doing the experiment in labor or compute or whatever it might be. And again, expense is very much in the eye of the beholder. So I know people that work in finance where an expensive function is one that takes more than 1 second to evaluate. But there's other situations like in climate where we might be talking hours. There's other problems where taking days to evaluate counts as expensive. I've heard of examples where months to get a single objective evaluation is something that can occur. So it's very much problem dependent what expensive means, but expensive in whatever context we're talking about. And I would say in general, with the main exception of machine learning problems, these are usually low or medium scale problems, by which I mean n is like order 1, order 10, order 100. Typically not more than a couple of hundred variables in most situations. And we will see that causes a problem, and Zaikun's talk will mention what happens as n starts to grow and how to make these things more efficient in that situation. I would also mention that this is kind of, in some sense, optimization for lazy people, in the sense that all the burden is being put on the people writing the algorithms. All they have to do is give code to evaluate f of x. They don't need to think about gradient evaluations. They don't need to think about noise or any of these kind of practical issues. They just say, give me something that's guaranteed to work for my problem. And certainly, inexperienced, lazy, time-constrained users is a valuable use case as well. And so I've given a few examples. There's this very nice survey article from 2015 that's related to the Nomad code that I'll mention in a little while, that mentions hundreds and hundreds of examples where these derivative-free problems arise in practice, including multiple patents and kind of very much real-world applications where this uses. And there's a nice textbook that lists a bunch of examples in machine learning as well. So there's many, many more examples if you're curious to take a look. Okay, let's start looking at some algorithms. And what I want to do is kind of provide just a nice little overview of what's out there. So the first thing I want to ask is, if we pick our favorite gradient-based algorithm, gradient descent, Newton's method, BFGS, whatever, and I use finite differencing to approximate the gradients, is this a DFO method? This is something you might have your own thoughts on. My personal view is no. The way I think about it is finite differencing is a way to produce gradients. In theory, they're inexact. In practice, we treat them as the ground truth, as correct. And you see this in the optimization library, say SciPy and Python. If you don't provide gradients, it will just do finite differencing, and then it will run a gradient-based method. So in my mind, I think of this as just a way to produce gradients. So I would consider finite differencing as not a DFO method. The exception is going to be a situation where you control the perturbation size, where you control the finite difference step size in a very careful, explicit way that takes into account these inaccuracies. So something like implicit filtering is a keyword to look up there, and we'll look at this in a little bit as well. This one I think is a little bit contentious. I think there'll be other people that I know that would disagree with me with this. This is my personal view for this instance. Next question, for those of you that know a little bit more about optimization algorithms. If I use stochastic gradient descent, or whatever my favorite gradient-based method is with stochastic gradients from like an empirical risk minimization problem, is that a DFO method? I'm going to say no, and I'm going to say most DFO people would agree with me on this one. A stochastic gradient oracle, for those of you who know what that is, gives you a gradient. It gives you a full vector with n pieces of information in it. They're inaccurate. They're random variables that approximate the true gradient, but they are a gradient. They represent gradient type information. You get it all in one piece. So I would consider stochastic gradient descent and its variance as a gradient-based method, with the caveat that the gradients are inexact in some way. There's some randomness that means that you don't get the perfect number. So that's my view. And I think in the DFO community, this would be fairly uncontroversial. Okay. Global optimization. For those of you know the different algorithms for global optimization, the majority of those are derivative free. The reason for that is gradients are local. They only provide information about how the function is changing locally. So for global optimization, they can be used to accelerate components, but in general, they're not really the key piece of information. And in general, global optimization methods usually assume bound constraint problems so that you've got a finite region, a bounded region, so that you can guarantee existence of a global minimizer. Now, comparing global and local DFO methods, it's the sort of trade-off that we're probably already familiar with in general optimization purposes. So for global, you get the benefit of getting a global optimum, which is usually what you want, but you need to explore the whole space. There's a theorem that says you need to explore everywhere. If you're doing local DFO, typically you will need fewer evaluations of your function, and you can exploit a good starting point. So normally you'll pick a starting point, you run a local method from there, and you'll probably converge to a local minimum that's somewhere close to the starting point if there's many to choose from. So you can exploit a good starting point if you've got one. Usually there's fewer evaluations needed because you're getting sort of a less good measure of a solution. And it tends to be more scalable as the dimension increases. So global methods tend to struggle once n gets above sort of order 10, maybe 20, 30, 40. Beyond that, it starts to struggle with the curse of dimensionality. I've been looking at local DFO methods this week, and the idea is they're going to be inspired by gradient-based methods. But in the interests of kind of giving everyone a nice solid starting point, I do want to look at a few different alternatives. So first alternative, evolutionary methods, evolutionary algorithms, genetic algorithms, these sorts of things. The idea of these methods is to mimic Darwinian evolution type processes. So what I'm going to do is I'm going to generate a bunch of values of X. They're going to be called a population. I'm going to evaluate my objective at each of them. And in some way, I'm going to delete the bad points, the ones with large objective values. By some metric, I'm going to delete them from the population. And with the remaining good points, I'm going to evolve them. I'm going to build a new population in some kind of random way. So by deleting the bad points, I might mean, I don't know, delete the 50% of points with the worst objective values, for example. And then I'm going to use the remaining good points to build a new population. One way, for example, you could do this is pick two random good points and take a convex combination that's weighted by the ratio of the objective value. So you bias the point that has the lower objective value, for example. But there's many different ways you could do this in different situations. It's an extremely flexible method because you just have to define how you delete the bad points, how you create the new points. It's very, very flexible for various problem types, and you can easily come up with your own ways of doing this. In practice, it's usually inefficient in terms of how many times you have to evaluate F to get there. They usually require very large populations, and it's kind of slow moving. But it is very flexible and a very popular approach. One nice variant that actually has a lot of mathematical theory underpinning it is something called CMAES, Covariance Matrix Adaptation Evolutionary Shortfall, I think it's called. And here we don't talk about the population in like an animal Darwinian evolution sense, but we think of it as a random distribution in high dimensions. So the assumption is your current population is drawn from a multivariate Gaussian, and you adjust the mean and variance of that Gaussian distribution as you evolve. So you can talk about things like, does the mean and the covariance converge to something like the function value and estimates of its curvature, for example. There's a lot more theory associated with CMAES. Another approach that I've personally had some good success with is direct, so dividing rectangles. This is kind of a branch and bound method. So what we're going to do is we're going to start with a bounded domain, and we're going to divide it up into rectangles of different sizes, and we're going to evaluate our objective in the center of each of these rectangles. Once we've done that, we're going to pick some rectangles and we're going to divide them up into smaller components. So here's an example that's kind of based on the original paper of how this might work. We're going to start with a bunch of rectangles and we're going to identify some that we want to subdivide. And once we do that, we're going to cut them, usually based on a rule of thirds, in some way to produce smaller rectangles. And you can imagine as this process goes on, these rectangles shrink in size. So we're exploring the space more fully. The two criteria we use to determine which rectangles to subdivide is either that the current center value has a small objective value, i.e. we think this is a good estimate of where we should be looking, so we want to divide and look more carefully in that region. That's called exploitation, zooming in on a good solution. The other criteria we might use is if the current rectangle is large, and there's various ways of quantifying what that means in context, but that's going to refer to the fact that we need to search everywhere. So if there's somewhere that there's a large region of uncertainty, we want to divide that up to shrink the uncertainty. So that's exploration, looking at areas we haven't checked very well. Exploitation is zooming in on areas we think are quite promising. So direct does it based on dividing rectangles. Another method that might be familiar to some of you is Bayesian optimization. So here, this is somewhat similar to the model-based methods I'm going to talk about later. But what we're going to do is we're going to sample the objective value to build a global model, a global surrogate model to the objective. And the standard way to do that in this field is to use a Gaussian process surrogate. I won't go into the details of what this is, but essentially this is where it gets the term Bayesian from. There's a Bayesian interpretation of a GP. But basically what it means is that the approximation that you get for your function can be described in some sense by a normal distribution. So there's a certain mean and a certain variance that measures where we expect the function to be at a given location. And typically, the uncertainty, the variance is going to be high if the point X we're considering is far away from the current set of evaluations that we have, because there's going to be a high uncertainty in what the function value is there. But we can construct a Gaussian process surrogate. That's essentially a global approximation to our function. And what we can then do is we can, given our easy to evaluate global approximation, we then maximize or minimize some quantity related to that to tell us where to search next. So this is a little example that I generated here. I've got the black line is my true function, the dots are where I've sampled it, and the star is the best point I've found so far. If I go and fit a Gaussian process to it, and there's plenty of software packages that will do this, you get a certain mean, which is the blue line, and I've plotted a 95% confidence interval to show you some measure of the uncertainty. And you can see the uncertainty is large when we're far away from any evaluations that we've seen. The uncertainty is small when we're close to evaluations. And one way you might measure where do we search next is something called expected improvement. This says, given the current normal distribution for my current value of X, essentially what is if I evaluate it here with this current distribution, what's sort of the likelihood, by how much would I expect that I improve on the best point I found so far, which could be formulated in this way. If you plot expected improvement for this particular Gaussian process, you get something that's very high where we might expect a local minimum or global minimum to be. But it also gets high in areas of high uncertainty. So at this point, for the next iteration, we'd pick this point, but maybe in the future, we'd pick a point somewhere over here to represent the fact that we need to search in areas with high uncertainty as well. So that's Bayesian optimization. And as I said, there's a whole Bayesian statistics interpretation for all of this. Direct search methods. As I'm running short time, so I'll try and get through this stuff a little bit more quickly. Direct search is kind of the other big local DFO method other than model-based methods. So what we do is we sample points in a neighborhood of my current iterate, usually based on some sort of geometric approach to pick new points. There's a very nice survey of many of these methods. There's three kind of generally used methods: Nelder-Mead, pattern search, and MADS, mesh adaptive direct search. Compared to model-based methods, these are usually less efficient in terms of how many evaluations it takes to reach a solution, but they are much simpler, which means the theory is much more developed. They can be adapted more easily to more complex problem types. And I put it usually because if you want them to work well, you normally accelerate them using the same ideas that I'm going to be talking about this week. So Nelder-Mead is probably the most famous one of these. This is sometimes called the simplex method, by which I mean the simplex method that's not for linear programming. What you do is you maintain n plus 1 points in Rn, which gives you a simplex. So for example, 3 points in R2, and you update it at every iteration. And the way you do that is you evaluate your objective at each of the corners, and then you rank them. So I'm using the star to be the best objective value, the dot for the middle, and the cross for the worst objective value. And there's different transformations represented by these blue and red simplices here. The standard one is where you take the worst point and you move it along the line that passes through the center of all the other points by different amounts. So you try evaluating f at each of these points and you pick the one that's the best, and you hope that you improve on the point that you found currently. If that doesn't work, there's a nice fallback where you shrink the size of your simplex by moving everything closer to the best point you found so far. It's kind of your backup approach. So it's a very simple method. It's been around since 1965. It's extremely popular because it's easy to understand, easy to implement. There's an example in numerical recipes, but there was work in the 1990s that demonstrates that it's provably non-convergent. There are counterexamples to convergence even in 2 dimensions. It does converge in 1D, but there are modifications you can make. There are sufficient decrease conditions, variations you can make to that does make it convergent. However, again, my experience in practice, this is not particularly good. Generalized pattern search is where you make sort of geometric perturbations around the current iterate. Basically, you pick finitely many perturbations around the current iterate. You accept any improvement and adjust your step size as a result. So you get a situation that looks something like this. You're at a current base point. You'd make perturbations, for example, northeast, southwest of a certain size, and you pick the one that gives you the best objective value. Now, for the mathematical theory, what you need is that of the directions that you move from, for example, plus and minus the coordinate directions, you always need to contain a descent direction. And that can be formulated in this way with this somewhat complicated expression. And you don't know the gradient, so you need to cope with the uncertainty in the gradient here. But you can do this relatively easily. And so you can either accept a point because it decreased the objective by a sufficient amount, or you can accept any decrease as long as all the points that you're going to visit in the entire algorithm lie on a rational lattice. There's different variations of this. The standard approach is to use plus and minus the coordinate directions. There are alternatives. More recently, people have been, including myself, have been looking at randomized search directions, which contain descent direction with some probability, and that does produce quite good speed ups for these particular methods. Mesh adaptive direct search is a variation of GPS, a variation of this method that is very well used in practice. And the idea is if we're searching now in, say, a box of a certain radius, we don't just take points from a structured like plus or minus coordinate directions, we take them from an increasingly fine lattice. So one approach is to generate these red lines that's just some random orthogonal set of directions and round them to the nearest lattice point. And the idea is that as you converge, this box shrinks, the radius that you're searching shrinks. And what you do is you increase the fineness, you shrink the size of the lattice faster than you're shrinking the size of the box. So it goes like the square, for example. And what that means is that as you shrink, you can get more and more search directions that sit on your lattice. So you get a much broader set of points you can explore. And mathematically, this gets very interesting because over infinitely many iterations, the directions that you're searching, the blue points, the pole directions, become dense on the unit sphere. What this means is that you can get convergence for non-smooth problems, problems with arbitrary constraints. There's a very kind of sophisticated mathematical theory that comes out of these methods. And there's a very popular software, Nomad, that uses this idea and then accelerates it with model-based techniques. So these are very sophisticated methods, and the Nomad is very widely used. And the last method, other method I want to mention is what they do in machine learning, which is where the dimension is usually very large. What they typically do is something akin to randomized finite differencing. So they pick a step size parameter h, and instead of doing perturbations along coordinate directions to get each entry of the gradient, they generate a bunch of random directions, think standard Gaussians, and they compute directional derivative estimates using finite differencing, and then they do a Monte Carlo estimation from all of that. This has the advantage that you can get a full dimensional upgradient approximation with very few evaluations of f, and then basically you just throw that into your favorite stochastic gradient method. In the theory, basically what you do is you need to prove error bounds on how accurate these approximations are, and there's various expressions you can get out of all of that depending on like the number of samples, the smoothness, the dimension, the step size parameter, and so on. So that's how that works in theory. But I just want to jump ahead to the model-based DFO, and I'll try and jump this relatively quickly. So here, the method we're going to talk about this week is we want to follow derivative-based methods, things like gradient descent, Newton's method, BFGS, things that work well in practice, but we want to replace any time we had a Taylor series or similar approximation with some other locally accurate approximation. So what we're going to do is, given a current iterate, I'm going to evaluate my point at various locations near xk and build a local approximation to the objective. And then I'm going to perform one iteration of a derivative-based type method to get my next step, and so on. And the idea in theory that we'll talk more about tomorrow is that if you pick good perturbations, good points near x to build the model, then the error in your local approximation is going to be comparable in size to the error from a Taylor series, which means if you throw it into a Taylor series-based method, the convergence theory is still going to work. That's the basic idea. And so we're going to look at this smooth problem where we don't have access to the gradient. But the main assumption we're going to work with in terms of f, again, like I mentioned before, its gradient is going to be L Lipschitz for some constant L. It's going to be bounded below by some lower bound, some global lower bound. And this is going to be enough to prove convergence to first order optimal points. I'm not going to talk about second order convergence, but that theory does exist. But the main point I want to mention for the purposes of looking forward is this Lipschitz gradient assumption gives us an error on first order Taylor series. So the error between the function and the first order Taylor series evaluated at the same point depends on the distance between the base point of the Taylor series and the point where you're evaluating things based on a constant L. Okay, so last few minutes, I want to not go into the details, but just trying to ask if we're going to try to modify a derivative-based algorithm to use these derivative-free models, which one should we use? There's many different ways you can minimize a function with gradients. And to do that, I'm going to look at just finite differencing. I'm going to go back to the thing I said is not DFO, but I'm going to look at the value of h quite carefully. So let's suppose I've got a linear model and I compute my gradient using finite differencing with some perturbation h. There's standard error bounds for these that will give you some control over the error in my gradient estimate. It depends on the dimension of the problem, depends on the step size and the Lipschitz constant. And so if I go through and do this and say, well, how accurate is my model going to be at some new point compared to my function value? Well, I can split that up into the error in a Taylor series and a gradient error term. And I get something that's based on the distance between y and my base point squared, and something that depends on h and just the distance between the 2 points I'm comparing. So that's the error bound between my function and my finite differencing model. So let's suppose we want xk plus 1 to decrease our model. Well, what we're going to need to do is compare what we expect to happen. So how do we know we pick a good xk plus 1 with what is actually going to happen in reality? So we evaluate our error bound at the point we care about. And now there's the question of, well, how do we pick h? Let's actually suppose we go to run our method. Well, if we look at this, we've got something that's proportional to the distance squared and something that's proportional to the distance. And given that the rounding errors in finite differencing can accumulate as h decreases, it kind of seems quite natural to take h to be as small as we can get to balance the two of the terms, but no smaller than that. There's no point shrinking h beyond, so that this term vanishes entirely, and we're just left with distance squared, because the finite difference estimate starts to break down from rounding errors. So a natural outcome from this would say we should pick h, our finite difference parameter, to be roughly the size of the distance we expect to travel in my iteration. This is going to be a problem, though, because we need to pick h to form our gradient, and we need to use our gradient to compute our next step. And we need to pick h based on the size of our next step. So we're in a bit of a circular loop here. How do we pick h before we know xk plus 1? Because we don't know how far we're going to be traveling. So what we can ask is there a way of running a gradient-based algorithm that allows us to know before we start our iteration how far we're going to travel in this iteration? And the answer is yes, they're called trust region methods. So it's one of the very standard classes of non-convex optimization algorithms. They're very popular. Your favorite optimization library probably has one of these available. And what we're going to do is at every iteration, we're going to have a current radius. And that radius is going to control how far we're allowed to move at this iteration. And we're going to set it based on how well our approximations have been performing over the course of the algorithm so far. So roughly speaking, how this works is at my current point xk, I'm going to construct a local model. So think of it, a quadratic Taylor series, for example, or a quasi-Newton approximation, some quadratic approximation to my true function. Then I'm going to minimize my local model. Instead of minimizing F, I'm going to minimize M, but I'm going to add a constraint. I'm going to say I can't minimize everywhere. I only want to minimize nearby to where I am now. I'll talk about how we do that tomorrow. I want to minimize our model locally. And then this gives us a potential step we could take. So xk plus sk is a new point that we may want to look at. But we don't want to necessarily move there. We want to check how good that point is. So what we're going to do is we're going to evaluate our function at our new point and compute this ratio rho. What rho says is take how much did I actually decrease the function divided by how much I expected to decrease the function. Now, because I computed s by minimizing m, the denominator is always positive here. So if rho is positive, this is good. This means f did actually decrease as we do it. If rho is negative, that means that we expected to go down, but we actually went up, and that's bad. So what we do is, based on the value of rho, we make a decision. If rho is good, if rho is close to 1, so that means that our actual decrease and predicted decrease are moving very close to one another, then we're very happy. We're going to move to our new point, and things are going very well. So let's trust our model a little bit more. Let's take bigger steps next time so we converge fast. If rho is positive, but not so close to 1, then we're still happy, but maybe we shouldn't be trusting our model any more than we are currently. If things are going badly, if we're getting very little decrease or we're going uphill, then we're not happy. We want to stay still and take smaller steps next time. We're not comfortable that our model is that trustworthy. So we'll shrink our trust radius. In practice, we're going to accept any step with any decrease, but we're still going to decrease our radius when things are going badly. And so for convergence, what we're going to need is that the model is accurate, like a Taylor series, and the way we compute our S, the way we compute our step calculation is sufficiently good. Again, I'll talk about that tomorrow. In model-based, this is exactly what we're looking for. The trust region radius is going to give us the radius that we need to search for. And so when we do model-based methods, this is what we're looking for. We're going to evaluate F at some points near our current iterate, and we're going to build a model that interpolates our function over this cloud of points. And once we've got our approximate model, we run a standard trust region method, but we throw away a Taylor series and throw in an interpolating model around this point. And then using some method, we figure out how to pick our next point. So I just want to show a very quick illustration of this as the last thing for today. So if I want to minimize the blue function, I'm going to pick an interpolation set. So for quadratic functions in 1D, I need 3 pieces of information. And this is going to be the radius that I search for. Given my 3 pieces of information, I'm going to fit a quadratic function in black. And I'm going to minimize it inside my shaded region, inside my radius around my current point. I'm going to go over here. That found me a nice decrease. This is a good point. I'm going to accept it. I'm very happy with this. And to maintain 3 points in my set, I might throw away this point in red. And I'm very happy. I take a bigger step next time. I've now got a model, new model. It's not as accurate, but it's still pushing me in the right direction. It's pushing me over to the right. So I'm going to take that new step as well. But now when I've got this new model, it sends me in the wrong direction. It sends me over to the right-hand side edge here because it thinks it decreases the model, but it actually doesn't. So what I'm going to do is I'm going to reject that step, but I am going to use it in my model. That does tend to help because it tells me where not to look next time. So I'm going to update my model, but I'm going to stay put. And now my model's very accurate. I'm going to take a step towards the solution. So I've got this collection of interpolation points that define my model. Otherwise, it's a trust region method slowly moving me towards the solution. Okay, that's all for today. What I want to talk about tomorrow is how accurate these interpolation models can be, how we need to modify the trust region algorithm, if at all, to ensure convergence. From a theory point of view, what's the penalty from losing gradient information? Is there a penalty from getting rid of gradient information? It feels like there should be because there's less stuff, but how do we do it? And how do we pick this interpolation set in a practical way? That's what I'm going to talk about tomorrow. But for now, I will leave it there. And yeah, a couple minutes for questions. Happy to stay around for a few more minutes afterwards as well, if we want to discuss any more.
Thank you, Lyndon. This is awesome. If there are any questions, now is the good time.
Looking quiet at the moment. I should say I will eventually.
Nadia.
Yeah.
Okay, so Linton, I think you mentioned at the start what kind of applications you are going to discuss in your presentations. Could you please just come back to them so that I will make some plan?
So I'm not going to talk about applications for the remainder.
Well, yes, you mentioned, yeah,
but,
okay.
Yeah, so I mentioned climate. That's one I've worked on myself. quantum I'm going to start working on soon. Adversarial example generation in the machine learning context. There's this sort of industrial optimization, simulation optimization. Sara probably will talk about more on Friday, and a whole bunch of others as we go. So yeah.
All right, and in the first application that's about the climate change, so I just was wondering if there is something there that probably would remind something like inverse problems. That's where you have to reconstruct from the value of the function, you need to reconstruct the input. Is there something like that there?
Yeah, I mean, it's a parameter fitting problem, which I guess is a very simple type of inverse problem.
Right.
It depends on the context. So I've done a bit of work in, say, optimization for imaging, and there you usually have exact gradient information because you might be trying to say, if I've got a noisy image, I might want to get rid of the noise, which is an ill-posed inverse problem. But there, the way you handle that ill-posedness is just by adding regularizers that have nice mathematical structure and gradients and everything. So it depends on the context for inverse problems. But yeah, I mean, parameter fitting is an example of an inverse problem, but
yeah,
whether it's DFO or not is context dependent.
Right. Yeah. Okay. Yeah. Thank you.
Do we have any more questions?
Lyndon, yeah, I have a question.
Yeah.
Yes. So just wondering, is that do you still get linear convergence for strongly convex problem for DFO?
I'm not sure. People don't really look at local convergence rates so much. I suspect you probably would in some sense, but it depends on exactly the variant of the algorithm and strongly convex with respect to what, linear convergence rates with respect to what metric, because the information that you use at each iteration can depend on the algorithm that you run. So if it's
right,
so normally for first order methods, for example, or Newton or something, we might talk about we get one gradient evaluation and maybe one Hessian vector product per iteration. Whereas when it's DFO, it's do we get a full resampled gradient every iteration? Do we have two new evaluations regardless of the dimension? So measuring convergence rates depends on the context. There's a couple of local convergence results that's from the ones I can recall seem to match what you get in the gradient base case, but that really hasn't been a kind of big focus of the analysis, just because for really hard problems, normally we're expecting kind of not necessarily to solve things to very, very high optimality. That's not usually what's desirable or needed for expensive problems, at least. And for noisy, it's unrealistic. So I think there are some results, but it's not as much of a thing, basically.
So does that mean that for DFO is usually like asymptotic convergence analysis?
Yeah. So it'll be kind of in the limit, the gradients go to zero, or there might be rates associated with that, but global rates. We don't necessarily assume there's going to be some neighborhood and things are going to be linear or superlinear or whatever after that. As I said, there's a couple of papers that look at it, but most people don't think about it.
Okay. Well, thanks, Lyndon.
Okay.
Well, yes,
Good.
That's it. And I just before Lyndon goes, I just wanted to tell everybody that as Scott mentioned in the chat, tomorrow and on Wednesday, Lyndon is going to start at the same time, and then the talks on Thursday and Friday by Zaikun and Sara will start a bit earlier, in particular 3 hours earlier. So just please keep that in mind.
Yep.
And we'll see you all tomorrow.
Yep. And for future reference, I plan on putting the PDF of the slides up on my website, and this is going to be recorded and I believe going to be put on the MoCaO YouTube channel as well.
We will absolutely put it on. Thank you, Lyndon.
Okay.
Thank
Thank
you,
you,
everybody.
everyone.
Thanks, Lyndon.